The second reaction, major reaction, is the Claisen condensation. And it is involving an enolate and an ester, an enolate and an ester. So you have 2 moles of an ester. One of them will become an enolate. So you will get, in the intermediate, you will get we're going to show you the mechanism, but first let's. And then, of course, when we protonate this, we get the beta ketoester. This is actually a CH. Very well. So this is called a 1,3 dicarbonyl one, two, three. That's why 1, 3. They're basically 2 carbonyl groups on 2 carbons, 1 and 3. Okay, and then this is called, like I said, a beta ketoester, which we talked about in chapter 23. You have a ketone and you have an ester. So what is the mechanism? Now, before we begin, notice that if we use 2 of these ester compounds, the ethyl, ET, OET, ethoxy is gone. So you only have 1 because, again, you had 2 moles. So let's look at the mechanism to explain. So we're going to switch this around and we're going to do OCH2, and then we have OET. So the first step, as you know, is to deprotonate and make an alpha anion, enolate. So we're using this base. And you have a CH2. All right, so we formed the enolate. It's in this form where we have a double bond. And now we bring the other ester compound. Remember, these come down. This attacks the carbonyl. And there's really not that much of a difference between the mechanism of this one and the one we've seen before. Oops, I mixed it up with the aldol condensation. So let's begin with here. We have OET. Make the O bigger here. I need more space here, that's why. Okay, so I'm going to also highlight so you can see what connections were made. All right, so here's yellow. This one right here. Or this one. Here's green. Here's green. So follow the arrows here. Now, the difference now in the mechanism is that, as this one acted as an electrophile from the aldol, is that the next step in an aldol would be to protonate, except here you don't do this. You encounter something we saw in the chapter 20 through 22, where this is actually a leaving group. So you formed the tetrahedral intermediate, where the electrons come down, and then this leaves. The ethoxy group leaves. So this is, got to write this down. This is the tetrahedral intermediate. Where OET is a leaving group. If you go back to the aldol, and let's go back really quick. You do not have a leaving group here. You have, we already said that these are bad leaving groups. So those electrons cannot come down and kick either a methyl or an H. Those are very bad leaving groups. However, OET, or ethoxy, ester, methoxy, etc., those are leaving groups. We saw that with esters. So our product will be CH. So it's flipped here. This is the same thing. So that's the Claisen reaction. And remember, we talked about how this can be stabilized via resonance if you, again, deprotonate the alpha carbon in the middle. So there are a few important points to remember about the Claisen condensation. Now, number one is that the reaction is also an equilibrium process, and then it could be reversible. Because the Claisen condensation does not give a good yield of the beta keto ester unless the product is converted to its enolate in the basic reaction mixture because of this. So we need, this to be in the basic nature, and the intermediate simply undergoes the reverse reaction, decomposes to give the starting enolate and ester. So it's not, it doesn't give a good yield. And what we can do, is we have some ways around this, but this is just an important point to remember. Now, the very important also thing to remember, you can make the reaction even worse if you have, no alpha hydrogen to deprotonate. So for example, this alpha hydrogen is hard to deprotonate. To begin with, and then even if it gets deprotonated, we encounter a problem when it reacts with itself, being okay. So I'm gonna show you what I mean. So supposedly we have this is you can see that now you don't have any alpha hydrogens here, no alpha hydrogens. Also here, which is actually needed to stabilize, because remember, when we have resonance and conjugation, it's better. So in this case, no alpha hydrogen, no conjugation. So let's go back a little bit here and show you what I mean. If we have resonance here, if we deprotonate and we have this, so this can go either way, and that creates conjugation. So we'll just draw one of those. And then, of course, it can go back the other way. So where I'm going to just draw it here. So this can come down. This can go. And that can go. So this actually drives the equilibrium. And makes the reaction yield the product.